Okay, so we're talking about the fundamental theorem of algebra. We're in 3.6 right now. It's what the fundamental theorem of algebra basically says is that every polynomial p of x, and you got a n, x to the n, the whole big deal, with complex coefficients has at least one complex zero. What that means is if you have a polynomial, there's going to be a zero of the form a plus bi. So we'll always have parentheses x minus quantity a plus bi, always able to factor that out according to that theorem. Gives us the complete factorization theorem. If p of x is in a polynomial with degree greater than or equal to 1, then there exist complex numbers a, c1, c2, c3, all the way up to cn, such that that polynomial equals a, some complex number, times x minus c1 times x minus c2. So what that does is it allows us to completely factor any polynomial over the complex numbers. Okay, so let's use that theorem to completely factor a polynomial. So we want to find all zeros, completely factor this polynomial. First thing I'll do is I'll note that x squared is common, so I factor out x squared. By the first two terms, I'll get x minus 3. Factor out a positive 1. That gives me x minus 3. What's common both those terms? X minus 3. What's left? X squared plus 1. Okay. But we know this thing can be factored here now over the complex numbers. Obviously we can't factor this as non-difference of squares over the reals, over the rationals, but we can write that down as, if I solve this, when it's x squared plus 1 equals 0, that happens when x squared equals negative 1. Square both sides, x equals plus or minus the square root of negative 1, which says x equals plus or minus I. So it's x minus I, that's for positive I, and x minus negative I, that's for the negative I. So this is completely factored. Oh, this is the zeros are negative 3, I, negative I, okay? And it also gives us the complete factorization of the polynomial p of x. Okay, so now we're trying another problem. A little bit tougher. I have x cubed minus 2x plus 4, clearly not easily factorable. However, what I can use the factor theorem to first of all find all the possible factors and remind our p's and q's. So plus or minus 1, plus or minus 2, plus or minus 4, those are all the divisors of that guy. Divisors of this guy are plus or minus 1, so my p over q's are plus or minus 4 over 1, plus or minus 2 over 1, plus or minus 1 over 1. Now, we're going to put each one of these in to see if we get remainder 0. I put 1 in, I get 1 minus 2, negative 1 plus 4, that's greater than 0. Let's try to get negative 1. Put a negative 1, I get negative 1, I get positive 2, that's 3, or 2 and 1, so that'll be 5, it's greater than 0. So I put in 2, 8 minus, well, there it is, 8 minus 4 plus 4 is 8, so that's greater than 0. And we want negative 2, I think negative 2 might work. I get negative 8, positive 4, and positive 4, so this equals 0. So we know negative 2 is 0, therefore we know we can factor this as x plus 2 times something. Okay? So the question is, what's that something? Well, we can use long division to figure that out. I put negative 2 here, 1, 0 for my placeholder, negative 2, 4. You know my remainder should be 0. Drop this down, 1, negative 2, negative 2. Positive 4 gives me 2, negative 4. Therefore, I factored as x squared minus 2x plus 2. Okay? However, this thing can be factored now. How do I factor that mamma jamma? Well, tic-tac-toe won't work. The quadratic formula will. So let's use the quadratic formula. So x equals negative b, 2 plus or minus the square root b squared, 4 minus 4 times a times c, all divided by 2 times a. 2 plus or minus square root. 4 minus 8 is negative 4, divided by 2. So this equals 2 plus or minus 2i divided by 2. Factor out the 2 and cancel, I get 1 plus or minus I. So now this polynomial will equal x plus 2, and I have x minus two things, x minus, and one is going to be 1 plus I, and the other is going to be 1 minus I. 1 plus I, 1 minus I, and if I distribute that out, I get x plus 2, x minus 1 minus I, and x minus 1 plus I. So I've now completely factored that polynomial over the complex numbers. Okay. So what we want to do is we want to break it down until we get some type of quadratic, and once we get to the quadratic, then we know we can break it down using quadratic formula. Okay, so the zeros theorem basically states that every polynomial of degree n greater than or equal to 1 has exactly n zeros, provided that a zero of multiplicity k is counted k times. So I've got a polynomial here. We're going to use that. Let's write this in factored form. First thing we notice, 3x is common to all factorization, all terms in factorization on the polynomial. So I'll get x to the 4th plus 8x squared, and I think I get plus 16, right? And I think we can factor that as 3x. This factors using tic-tac-toe or any method of that sort. I think you get x squared plus 4 times x squared plus 4, which is x squared plus 4 squared. Okay. Recall that this is degree 5 polynomial. This is a degree 5 polynomial. Okay. This thing can be broken down using quadratic formula or just solving this equation. X squared plus 4 equals 0. X squared equals negative 4, or square root both sides, which plus or minus x equals plus or minus 2i. So this will equal 3x times x minus 2i, x plus 2i, which is equal to 3x, x minus 2i squared, x plus 2i squared. Now, 0, when x equals 0, it's a 0. So 0 is a 0 of multiplicity 1. 2i is a 0 of multiplicity 2. And negative 2i is a 0 of multiplicity 2. 2 and 2 and 1 make 5. That's what this theorem says. Okay? It has exactly n zeros if it's degree n. This here has 5, degree 5, so it'll have 5 complex zeros. Okay, so in the last problem, you notice that not only do we have one conjugate, but one complex number, but we had its conjugate as a 0, and that's actually always true. And it comes down to the conjugate zeros theorem. If you have a polynomial with real coefficients, and if the complex number, say z, is one of the zeros of b, then its complex conjugate is also a 0. So recall what a conjugate is. The conjugate to x plus 3 is x minus 3. The conjugate to x minus I is x plus I. The conjugate to x plus 1 plus I is x minus 1 plus I. So those are conjugates. Okay, so if I have a complex number, this is its complex conjugate. So I have x minus I, its complex conjugate is x plus I. If I have x minus 3 plus I, it would be x plus 3 plus I as its conjugate. Okay? That's wrong. So if I have I as a complex number, its complex conjugate is minus I. And if I have 1 plus I, its complex conjugate is 1 minus I. Okay? So this is how we find complex conjugates. Okay? Notice that it's just you change the sign in between the real number, the real part, and the imaginary part. So suppose I want to find a polynomial of degree 3. It's got 3 zeros, okay, 3 complex zeros that has integer coefficients, and 2 of the zeros are 1/2 and 3 plus I. Then we know that we can write this polynomial, p of x, is some number a, I don't know what this number a is, times x minus 1/2, because 1/2 is 0, x minus 3 minus I. But if 3 minus I is a conjugate, then we know x minus 3 plus I is also a conjugate. And then what you can do is you can multiply this thing out, and you'll have exactly what we want. Okay? So that's how we find polynomials that have given zeros, because we know if we have one of them, we have its conjugate. Okay, so now we have the linear and quadratic factors theorem. Basically, it says every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. What that means is that I can factor this thing down into x minuses, and then these quadratics like x squareds, right, that are irreducible over the real numbers, meaning that if you had to break it down, you'd have to use the quadratic formula to make them complex. So let's kind of understand what this is exactly saying by looking at this example. So we have x to the fourth plus 2x squared minus 8. We know we can factor that as x squared plus 4 and x squared minus 2. X squared plus 4 can't be factored over the real numbers. It can be factored over the complex numbers, because we can solve that with i's in them. This we can, because if we set that equal to 0, x squared minus 2 equal to 0, that happens when x squared equals 2, or x equals plus or minus the square root of 2. So x minus the square root of 2 and x plus the square root of 2. So what I've done is I've just done exactly what this theorem says. I've broken this polynomial down into linear and an irreducible quadratic. Okay, that's what this theorem says. Okay, so what I've done is I've broken this thing. Let me take a look. I've broken this thing down into an irreducible quadratic, x squared plus 4, and two linear factors, x minus the square root of 2 and x plus the square root of 2. Okay, those have real coefficients. Okay, real coefficients. But suppose I wanted to factor that polynomial p completely into linear factors with complex coefficients. In other words, if I want to keep going, you can keep going. Okay, so this theorem says you can break them down this way, but we also know the complete factorization theorem says I can now break this down even further, and we know that if I set this equal to 0, subtract 4, square root both sides, get 2i and negative 2i. So it'd be x plus 2i, x minus 2i, x minus the square root of 2, x plus the square root of 2.